form of.
Well, I think eventually they're going to. My classroom is going to be one of the, I guess what you would call the
Test bed.
distance.
Oh, online. Yeah.
Well, we have 4 colleges,
Huh?
and only 2 of the colleges have a physicist.
Oh, they have physics program, you mean?
They have somebody actually.
Oh, somebody who can teach actually.
Somebody with a degree in physics.
Got it. So others try to do it online. Then this works fine for those cases, right? Those who want to be in the class, they stay in the class. Those who don't want, they.
But I'm kind of demanding setup.
Yeah, you're on camera, just making you.
Well, so you know, for now, this is for you. That is somewhat convenient. My setup isn't as convenient, so they're putting in a laser projection system and a screen in the back. So if I have multiple students at multiple places, not only can I see them, but I can see what they see to make sure that there's not a technical issue.
Exactly.
And
And what I do is, like, when I was at home, I was projecting it on my television. That's how it started, kind of. But I do this in another classroom also. So I use exactly what you say. There is a projector there, so they don't have a television. So I just project this screen onto a wall, basically. But you are saying, what you're telling has a point that in that kind of system, I don't see what they are seeing, right? And that leads to an issue of, oh, am I writing in the right place and those kind of stuff. So it would be nice if I can bring out what they are saying also, which is what you're suggesting.
yes,
So yeah, good point. Yeah.
they actually they had consultants from CEW who are setting this up.
So is this this will be common for all community colleges, right?
Oh, we're kind of a weird system because we're such a small population area, but politics has 4 colleges. So what I'm trying to do, and I'm the only one. As far as the 2 people with physics degrees, I'm the only one that has.
Hey Jordan, how's it going?
Hey, what's up?
Sustainable class.
Oh, you can see me.
Yeah.
The guy at the other school actually had to teach
It's
bowling.
facing this way.
He had to teach a bowling class to make his course work.
Wow.
I actually had to cut back and turn classes down so that I could do this.
So since you said you're right on the sort of at the border, right? So is it Illinois Community College or is it?
We're Illinois.
Okay.
We're about 35 miles from Vincennes.
Okay. So it is not under a single board, because my wife teaches in John A. Logan.
Okay.
And she did say that they invested a lot of money into all this IT stuff. But it seems like more than SIU, but that's a matter of how you take decisions.
I would have, John A. would have been probably my, if I had, it would have been my first choice. I'm very familiar with it. Back in the day, my sister was in the basketball program, and so we knew the coach really well and a lot of people. And I really like the school. I can't complain where I'm at.
Yeah, the idea is to serve the community, right? If everything is perfect, then what do we do, right? That's another way of looking at it. So
Well,
if it's not perfect, we have some more to contribute.
That you have to consider that there's more around John A. as far as things to do than where I'm at.
I can sort of imagine, especially after we say it, I can sort of imagine. But again, that doesn't mean that I have a correct perspective.
So today's the day I have to slip out.
Oh, yes.
So what's the population of the town?
We're like less than 9,000. 7,000 of them are related.
You know, no, one of my classmates, so, she said, like, at the town where she comes from, there's like 150 people and 150 people and a church. That was the town, and everybody was related to each other. Like it was like that's my cousin, that's my second cousin kind of thing.
Nice, nice. So this is back in your Nepal or
No,
here?
no,
Or
no.
here?
Here.
Okay, so we have Luke, Jordan, and Elliot. 3 plus 3, 6. Which is the class that has 8? No, this is the one that has 8 students. So you're missing 2.
Yeah. We're missing.
Oh, Michael. What happened to
and-
Michael? Yeah, just give it.
Probably.
Let's give it half a minute or so. It's already 4 minutes. I take time anyway. But
Did you get my
I did. I'm so sorry. I never responded. I apologize. Yeah. What was your question again?
What is he using for his text and what, did he have a page?
Yeah, he does have a, yeah, I will send that to you. It's called QNet. All right, I'm down. Yeah, he's got a page. He covers quantum computing stuff. The page is really good. It's got lots of resources. And then we are using a text. It's not my favorite. It's Valentine, Leslie Valentine.
That's one I'm not familiar with.
Okay, yeah, I wasn't either. Yeah, I have a PDF of the first edition, which I can send you as well. Yeah, it's not, I don't know, we do the homework in that book, so I use it for that, but it's not my first go-to.
Well, by the way, I did find a brand new 1953 copy of the Methods of Theoretical Physics.
and
$1,900.
oh, this is the Molson Freshman.
So
This was
Molson Freshman.
a brand new unreleased both copies, both volumes.
so that book was printed in 1953.
I think it was reprinted, but I think 1953 was maybe one of the
Hey,
first.
it's lost the value then.
But it was I have the PDF of the copy, but yeah, there was an antique bookstore that was selling it more than I was willing to pay for it.
That's ridiculous. But there's a lot of scam out there also. Like you will see a lot of books that are not even books. And then, like this is often happens with PhD thesis, which is out there open source. They will say that this is for sale. Like most of the people's PhD thesis is for sale on Amazon. So I think a lot of it is a scam. I guess many people just spend money.
Since you mentioned an old book, my parents just recently moved to a new home, and they used to live in a small town in southern Missouri, and there was a lady who I guess probably 40 or 50 years ago passed away, and she was a librarian. She had a bunch of old books, and she had like an old chest full of just books from like the 18 and early 1900s. And we were going through the books the other day. I found this gem. See if he can. It's a textbook of physics, Wentworth and Hill, and the book is from 1905, I think. So let's see if I can. You see here,
Yeah,
it's going to be backwards, but
before 1905.
Wow.
Hard to read yet.
1898 was the original edition, and then this book is from 1905. So it's kind of neat because, you know, just seeing the drawings and the notation and stuff they use, it's kind of cool.
Yeah.
Did you not bring one of those old books written in German in our class, like last semester?
I don't think so.
Like it was like really small book.
I had a lot of books. Like when the university that I was going to before this had, I guess, a big giveaway of, they had a bunch of books that they, couldn't use anymore. So I took basically every book and filled an entire bookcase. Let's see if I can show you. So this bookcase is nothing but physics books. So all from the university. So it's kind of neat. Sometimes I find some gems in there.
Nice. Okay. Midterm 1, it will be open sometime on Monday, and it will be due 1 week. So 1 week from next class. But that doesn't mean that there won't be any homeworks in between. This is not supposed to be a very long midterm. This is just a normal midterm. We will go through the usual homeworks as I'm going. So there will be overlaps of this with homeworks. And for all I know, most probably there will be a homework due on Monday at that time. So be responsible about how you plan your homework. So homework 4, since I will have 2 classes. No, am I teaching on Monday?
I don't see why not.
Why not? Right? Good.
I like the idea of teaching, that way we don't get behind.
Class on Monday, right? So just an announcement, class on Monday. So that way I get 3 classes. So then we do have a homework on September 14th. Most probably I should be able to finish this by.
So you're assigning homework for today, and it's due on Monday.
Yes. No.
It should be 21st, right?
21st, you mean?
Oh no, sorry, 21st. That didn't sound good. Okay, I'm just assigning it now. No. Sometimes I'm that mean, but okay. So yeah, so this is September 21. Yeah, thank you. Okay, so we have been talking about where we ended last time is continuity equation, and that's so I'll go over that a little bit more because that's sort of one of the central equations that I want to keep for about a few weeks. And the main idea here is that in electrodynamics, in the introductory level, you're pretty, most often I'm pretty, at least the standard is that you think of charges as a central player. And this is the same in gravity also. You think of masses as the central player. And there is a gravitational field, or if you're talking about charges, there is a charge as a central player, and there is an electric field associated with it. And the way it goes, especially if you go back all the way to Newton, there was no gravitational field, right? It was just force m1, m2 over r squared. And you can get almost everything done with that. That's the important point. And you don't need to introduce this g, right? Small g. A gravitational field that's there everywhere around. Same thing here. You can get away pretty much a lot of without introducing the idea of electric field at all. But since Faraday, it is very clear, or I would say there is a lot of indication that electric field is not just a mathematical construct. It is actually a physical quantity. And by physical quantity, we mean that it has momentum and it has energy. So the moment I talk about, so fields, let's say electric field, E and D, right? So the main idea is that E and D, which come together, right? The moment you put in charges, and let's say this has some motion also if you want. So this is V1, it's just a random configuration, so that's V2. So because there are charges, it creates electric field, and because it is moving, it creates magnetic field. Right? That's a simple idea we have, and there's a, at least I can draw the electric field, right? So this is the electric field. And the question is it really necessary, right? Is there any physical content in there? And the point is no, these are actually, so every volume of this space and time actually has energy associated with it, momentum associated with it. So that's the physics of this, and we want to capture that. So E and B, so every volume element in space, right? And for every time has energy and momentum. And just that idea should make you guys start thinking, is that really true? You should start questioning that, is that really true? How can I verify that claim? And that is how we will try to understand this the subject as much as possible. It gets a little harder because charges are not the central points, and that is where the continuity equation comes in. So I'm going to write an arbitrary continuity equation. Last time I wrote it for current, and afterwards I felt that there might have been a little bit of confusion, or generality was lost. So let's say a general continuity condition, and then we will do it for different fields. So continuity equation is, it could be any quantity. So let's say C, right? So that is a field C of R as a function of time. So this is a physical quantity. Remember that last time we talked about the charge density, but this time I want to keep it arbitrary. It could be anything. Think of this as mass. That's a good mass density, for example. And let us say that is a vector. Let's call that something that doesn't come very often. Let's say E. E of F, right? No, E. So this will be called a flux of C. Okay, so there is a quantity C, and there is another related quantity E, which will be defined to be the flux of C, and we will sort of try to understand why flux, the word, is appearing. And let's also introduce one more, and that's S of R and T. And this will be a source of C. Source or sink, actually, I should add. Source or sink of C. And a continuity equation for this quantities could be, let me know if I'm out of the board, C by dt plus and we will try to write it as S on the left hand side. It's awkward to write it on the right hand side also, but we will try to keep everything on the left hand side. And actually, I should, now that I'm talking about this, I should also point out, how many of you have been using the copies of the chapter that I put on the on Teachable? Was it useful? Should I be doing that? All of you guys have. Do you see what I'm talking about? The Triggers book, I put the copies of chapter on the.
I think the whole book is available online, so
Yeah, I
mean, I shouldn't be saying that.
I like the idea. I haven't used it just because so far I've felt okay, I guess, with this.
Okay, so yeah, so I'll keep putting it in there, and I'm allowed to do that as far as I go chapter wise in there. And I wanted to say that because this is at least this part where I'm going, it is in the chapter 3 of the book, so it's a good thing to read Schwinger's book. So it begins with this treatment. Okay, so this is the, as we see, is the rate of change of C. This seems like there is a divergence of the flux, and then we have a source. So how do we interpret this? This is a differential statement of the continuity equation. Immediately integrate this over any volume V. So let's say there is some random volume V. So this is volume. And you integrate this over this volume. This could be small, big, doesn't matter. It could be the whole space for that matter. That's also perfectly fine. So that's the volume of V of C over dt plus this is E plus is equal to 0. Whatever this C must have, if we say is a density, for example, if it's a charge density, if I integrate over the volume, I get the total charge, right? If this is small c, I'll make this capital C, d by dt of capital C, okay? So capital C is, so this is capital C. Capital C is equal to integral of small c. This is over the volume. It's like if this was charge density, that's charge. Hopefully that's clear. And this is using a divergence theorem. This is only on the surface. This is dA dotted with the flux plus, let us say again, this is a total source, or let me call it capital S. Capital S is equal to sum of all the sources, right? Whatever is getting created. And then the interpretation again comes, so this is the same volume. And if you want to talk about how much is a quantity C changing with time, how you would go about this. So this is a rate of change of C, right? Rate of, like it could be population rate of change of population C. For that, you would say, you could take it on the right hand side if you want, and then say that ask about how many people are born and dying. That's a source, right? Inside this region, how much is C is appearing out of nowhere, or how much is disappearing into something. That's one thing. And we also have to worry about the surface. At each point on the surface, there could be C coming in and going. And in that sense, it is a flux. Right? So this is a flux of a quantity going. So it's a flow of C. So in that sense, so E is the flow of C. So if it is a charge, the flow of charge will be called a current. If it is a mass, the flow of masses is called velocity, right? Is there a special word for it? Extra credit. Is there a
Flow of masses.
Yeah, when there is a water flow in fluid dynamics, if water is flowing, is there a special name for that? Flow of masses, because at each point you associate a velocity to it. Is there a flux of what? Yeah, check out extra. I like this way of getting extra credit where I don't know the answer. I just put it in you guys. So extra credit is what is the flux associated with mass density called? Is there a word or not? Because this idea of continuity equation came from fluid dynamics. And that was a nice thing that they saw that electrodynamics, all the fields can be thought of as a flow. Like electric field can be imagined to be a flow. Question, yes.
Do they call it like water current? I've heard of that word before.
Water current. Check out. Yeah, fluid current. Yeah, check out. I don't know. Yeah. It doesn't ring a what current doesn't ring a bell, but then I don't know. Okay, so yeah, good exercise. So that's how we should interpret.
Excuse me, doctor.
Yes, please. Yeah.
There is an example of change in mass, rate of change in mass, since the mass is not changing. But I remember there's an example of mass changing where there is a rate of change when the rockets are going away from the Earth, where the fuel is inside the rocket, and the rocket is what do you call it?
Oh, you're saying yes. When there is a rocket.
The exhaust.
Yes. Yes.
No, I mean the rate of change in the mass of the rocket when it was before that, the mass plus the fuel inside it, and then the what do you call the exhaustion of the fluid outside the mass of outside the missile or the rocket.
That's correct. That's correct.
Yeah,
And that
yeah.
example will fit
That
in.
example of
Go ahead.
that's I think it's are we talking about the same thing, that rate of change in mass as an example of that?
That is an example, but the only thing that is missing in that is that there is no source of mass there. Right? Mass doesn't appear from nowhere. Whatever you're losing, if you say the system is your rocket, correct? The mass is going out of that system. So it is crossing a boundary of your volume, right? That's a good example, but at least I don't see a source there, a source of mass there. So typically when you do Newtonian mechanics, mass doesn't disappear, right? Typically masses don't disappear. And even, so this is what, okay, so maybe this is a good point. So this is where you're going to take a change. As of now, I have been talking about charge density, mass density, very intuitive, very matter associated, right? We are very quickly going to talk about electromagnetic energy. Okay, so that's no more matter. And then we have to talk about what is the source of that. What creates electromagnetic energy? What is the flux of electromagnetic energy? That's what we are going towards, right? So this is a familiar example. So I'm beginning with that, but very quickly I'm going to jump into more fluidy concepts, more fluid-like concepts. Correct. So that way, did I clarify? I think so. Right?
Yeah.
Okay. And there was a discussion about whether this should be on the right side or on the left side. And I last time insisted that no, it should be on the left side. But now it's a matter of which side you take as positive. When you think of this as a divergence theorem, outward is chosen to be positive, but then probably you can, if one argues that no, I want to switch that, then you can keep it on the left hand side also. So as far as you know the interpretation of that, I think it is okay to keep it either way. I think I came out a little strong last time that no, it has to be on the left hand side. But we will keep it on the left hand side and interpret this as a source, sorry, as a flux. That's all. And for charge density, of course, and you guys did an example also. This is d rho over dt in your homework. And this is del dotted with J. And notice this is not an approximation. If Maxwell equation is correct, this is correct. Right? If you believe in Maxwell's equation, which experiments has tested to great accuracy. In fact, if you take the quantum version of the Maxwell equation, that is the most accurately or most precisely tested theory in humans have created. It has been tested to 13 digits. No other theory has been tested to 13 digits. And that's also related to your homework. There was a, what is called fine structure constant. Fine structure constant. If you check it out, extra credit again, right? Extra credit. This is a good thing to know just for information. Tell me what is alpha as accurate as people know. And it is known to 13 digits. This is the most accurately measured physical quantity ever. Right? So this is known to 13 digits. And you can, since it's an extra credit, instead of me telling that, you can say, give me another physical quantity that is more accurately measured. And it doesn't exist as far as I know. Okay. So it's kind of a interesting stuff. So in that context, if you look at the continuity equation,
So
assuming that
I have a
yes,
question about what you just said. Well, what about pi?
pi is not an experimentally measured quantity.
Can't you measure it? Maybe not.
Yeah,
You're right.
so
Right? It is a theoretical. It's a theoretical concept, right? Pi, yeah, that's. How do you answer that? Yeah, it's not experimentally measured. Yeah.
Isn't pi just the ratio of circumference over the diameter?
Yeah, but has it been experimentally measured? Have you measured experimentally? Probably it can be measured.
I think that's how they got it.
Yeah, so how about this? Can you measure the area of a circle, right? Area of a disk to 13 digits of accuracy? That's a question you can ask. Right, I'm not sure exactly. Yeah, so these are, so when you, for example, if you are in a committee which is deciding on unit systems, you would say which is more accurately measured? Is it the fine structure constant, or is it the length of a rod or a length of a disk? Can you measure the length of a rod to 13 digits of accuracy? When I'm asking myself, actually, it might be possible, but apparently not. Let's check it out.
I think we can go only up to 8th digit.
Okay, very good. So I now.
Because isn't that how we define length?
Length is these days defined using the wavelength of light, right, of certain particular light. Yeah, good thought. I would say you guys think about it. I'm not qualified enough at this point. Say I'm myself a little. I can narrate something that was interesting. It was realized only recently. So various quantities are you make experiments, and then it gets more and more accurate. And remember, gravity is one of the oldest theory known, where we have an equation. By theory, I mean you have 3 physical quantities and you relate them together, and we say that that is true. F is equal to gm1 and 2 over r squared. But everyone took this for granted, the gravitational force, and no one checked this, how far this is true. So in 1999, there was a theory that was suggested that if you might be aware that there are theories that propose that there are extra dimensions. And if there are extra dimensions, why don't we see it? And then typically the answer is, oh, they're so small, we cannot see it. But then in 1999, there was a proposition that actually extra dimensions could be as large as a micrometer. And if that is correct, then gravitational force should see it. We should be able to see that at that scale, gravity doesn't work. But then it was realized that gravity has never been verified to a micrometer. It was verified only to a millimeter. It was only then it was realized. And then immediately experimentalists said, oh, okay, we need to do this. And it was WashU in St. Louis that took the lead, and they immediately, almost, it was very straightforward to do that. Within a few years, they tested it to very good accuracy, and then the extra dimensions didn't stand that verification. So yeah, so sometimes it is surprising that certain things that one would think that is should be well known is not well measured. And so the point is, alpha, to my knowledge, is the most accurately measured quantity. I actually attended a talk from that lab. This was in 2010. No, before that, I was a grad student, like 2006 probably, and that when they made the increment to the next 2 digits. The theory took about 10 years of calculation, one calculation. Think of, we do calculation for 2 pages, homework goes for 2 pages. This goes on for 10 years. Okay. So, I mean, it Feynman diagrams, which was really long, and that was a theory, and then the experiments was for the precision. So that was the important. Anyway, so my point again was that, so if Maxwell's equations are correct, this is correct, and if you compare these two, this means to say that there is no source for charges. So whatever we have, charge is conserved, especially for the whole universe. I can immediately say that this volume is the whole universe. I don't expect, and if we assume that there is no exchange of the flux there at the surface of the universe, then we are stuck with whatever charge we have. If it is neutral, it is neutral. If it is charged, it is charged. So that's continuity equation for the charge.
You wrote a lowercase j there. Is there a reason for that?
No, actually, I keep changing. Sometimes I write small j, sometimes I write big J. Did I write big J before?
No, but I think on the homework you had big J's. And
Capital.
Use both in the homework, actually.
I see. Yeah, I think as far as I know, when I started, I think this typing these homeworks a long time back, I think I was for capital J, but these days I'm for small j. So I prefer to use small j. So this homework's probably some of them might be old. So maybe the units are the older ones I remember. So maybe there it is j. So yeah, I should correct them and make it uniform sometime. But so let me, since we are all of us here, so let's survive with the j could be capital or small. Go with the context there, or if there's a confusion, ask me. My apologies. Yeah, there is a confusion. Okay, so that's the first conservation equation we have, right? Conservation for of charge, and I want to build more of them. So what? Oh no, 11:30. Yeah, it goes all the way from. What happened? Set this camera to me. So we want to talk about another conservation equation, and for that we talk about conservation. So we'll derive this. Remember, if Maxwell's equations are correct, anything derived from that has to be true. So we will derive it from the Maxwell's equation. So conservation of electromagnetic energy. Can also say electromagnetic energy density if it is local, but electromagnetic energy. So before that, maybe we should remind ourselves. So if there is a volume, that's volume V, and there is electric field in a certain region, right? What is the energy associated with electric field, which you should have seen before?
Electric potential, is it?
No.
And
Yeah.
have epsilon naught E squared.
Yes. So if you think of a capacitor, right? You often do this calculation that if there is a capacitor, there is an electric field, right? There is a uniform electric field in there, and then you ask how much energy is there. So energy density, basically. So energy density energy per unit volume is equal to, if we are in vacuum, no material, so that's epsilon naught E square plus half, often we write it as B, right? E square over mu naught in the denominator. We will give it a letter. Again, sometimes I use U, sometimes I use capital U, but this one I'm still confused. I don't know which one to use. So this also changes with, on a daily basis. Let's say small e. So this is equal to, you can also write this as E dotted with D plus half of H dotted with B. Right? That's clear because we had those relations, right? D is equal to epsilon naught times E, and D is equal to mu naught times H. If there is a material, these definitions will still go through, but then these are not vacuum permittivities and permeabilities of the material comes into the picture. So this is just to remind you. And what about, so usually there is a energy density, which we have already come across, but I'm going to give an equation for this now, apparently. And then you would say, what do you mean by flux of energy, right? That means flow of energy. Right? So this is, notice everywhere, right? This, imagine this to be a fluid. Right? So it's moving around electric field lines. Think of it as a fluid if you want. And now we want to talk about flux of U. Okay? And again, this is supposed to come as a consequence, but since we have already seen it, I want to give you a feel for it. So flux of electromagnetic energy. And that also I say you have seen before in your introductory physics courses. It comes in a small segment, but it does come. Anyone?
E cross H.
E cross H. Correct?
Pointing vector.
That's called a pointing vector. So this is E crossed with H. And this is, maybe this is not very familiar, but this word for some reason, I think, rings a bell, I guess, pointing vector. Where do you see pointing vector? which, let's say, because these days the introductory level physics is so regimented, everyone goes through the same chapters. Which chapter of the introductory level? Sad that everything has been chapterized. In which context do you see the pointing vector?
It's up in classical mechanics, right?
Classical mechanics, so maybe, yeah.
I saw that in E&M.
Yeah, in electromagnetic waves. Right,
It's in the
usually-
Maxwell's equations.
Yeah, Maxwell's equation, and that's when the electromagnetic waves come by, and then you talk about E cross H has a meaning. And it's kind of a nice name in the sense flux has a direction associated with it, but this is actually the name of a person. So it's just like he was really
It's aptly named for what he produced.
sort of. Yeah, I think so. Yeah, again, very trivially speaking. Okay, so those two apparently are connected according to. So that's what I'm claiming. And then you would like to know what is the source of electromagnetic energy, right? What if you want more electric field? What would you do? Right? So clearly have more charges here, right? So more charges will create more electric field. So surely something to do with charges, but then magnetic field is also there, right? Magnetic field requires maybe current. So we want to see exactly how that is. We can only speculate at this point. So let's depend on Maxwell's equation and fiddle around with it. So let's start with Maxwell's equation, and I will write the Maxwell's equation. So let's write it down. So del dot it with D is equal to rho. So usually we say epsilon naught times E. So this is D. Del dotted with B is equal to 0. Sometimes it is convenient. I'm not going to do it. So this is dotted, right? If you want. This is rho E, rho M. If there was a monopole charge density, that's where it would sit, right? But it is 0. It doesn't exist. So it's dotted. If it was there, that is kind of nice. It helps to see how this will change. So del cross of E plus dE by dt is equal to I want to write this as is equal to 0, right?
Yeah.
But I want to write it as minus. Since it's a 0, it's anything. But then I get to write this as dotted.
So I noticed you did that on the homework too. Is there?
Oh, did I? Oh.
What's the insight to doing using minus instead of?
Oh, what's the insight? Yeah, good point. Yeah. So yeah, let me finish this writing. Yeah, good point. So I think I can. That's a good thing to find out. So this is minus, right? E. This is JE. Okay. Now it turns out, and this has again at a fundamental level, people look for symmetries, right? Any time you have a symmetry, that means there must be some meaning to that. And it was observed that if you were to change the electric field, so start with Maxwell's equation, and there is another universe in which there were another set of humans, and they found it convenient to call the electric field the magnetic field. So you switch all the electric field to magnetic field to begin with, and you switch all the B to minus E. Notice this minus sign, and as far as I know, it doesn't change equation. Oh, and I have to do something more, right? So rho E goes to rho M, and rho M goes to minus rho E, right?
I have one question. So are those like anti-symmetric properties or anything?
They are not, okay, maybe it is antisymmetric in some sense. They're called dual symmetry. Now, yeah, it is antisymmetric, right? And so suppose, and the way to see the thing is, if you construct this to be a vector, right? So this is E prime. So in fact, okay, so this is the symmetry that is observed. That is obvious enough if you look at it. You can look at it, but in fact, this is a bigger symmetry. So this is what I'm saying. This is actually a rotational symmetry. So some angle, not rotation, some rotation in some space of electric field. This is probably not obvious to you when you look at it, but if you were to make this transformation, right, Maxwell's equation stays the same. Right? So this is called dual symmetry, but dual symmetry is only when you write it in this form. But it was very quickly realized that actually the symmetry is significantly bigger. There is a whole rotational symmetry in that. And we just happen to be in phi equal to 0. Right? So then you always say, why should I do that? I mean, a choice by an observer should not matter. We should have the independence of that choice. And usually, whenever there is such a symmetry, there is a conservation principle all the time. But remember that this happens only if you introduce a monopole. All these are very, very compelling reasons for a theoretician to claim or to speculate that actually monopoles exist. It's just that we have not seen it, and suggest experiments where you might be able to see. But it is true that even after a significant amount of a bias towards expecting that it is there, experimentally it has never been seen. So it has eluded. So until you see it, it doesn't exist. Right? That's a fact. So we want to keep trying. And then that leaves us with the mystery of why this, why is phi equal to 0 for us. Right? So that's a kind of a good question actually. So that's why I chose. So that symmetry is what guided me to put that negative sign. Okay. So okay.
See, I thought the minus sign. So I thought, Lenz's law. I thought it would have to be minus del cross E plus partial B partial T, because isn't Lenz's law like LE in?
Oh, Lenz's law is when it is 0, right? So Lenz's law only says that relative to this is negative. Right? So Lenz's, okay, maybe what you're saying is this is del cross E. Lenz's law is only this, right? Minus dt by dt. This sign is kept. You're not destroying them. So relatively, they are of the opposite sign. If I put an equal sign in between, relatively they are of opposite sign. If I say this is negative, that's positive, right? If I put it on the other side.
Okay.
So it's like saying that this negative sign is this side. Maybe that's so. Does that help? So Lenz's law is obeyed, of course.
Okay.
Yeah. Anything that we already know in introductory level physics cannot change for some suitable reasons of a theoretician kind of. So yeah, so that should be, I mean, Lenz's law is important, very important. Helps?
Yeah.
Yeah, but that's it. Good question. So, but for us it will be 0, but it sort of guides us with the signs. Okay, so if that is the case, so let me take a dot product of the last equation with electric field. I can do any manipulation I want with this Maxwell's equation and learn something new. And on here, let me dot it with a magnetic field. Sometimes one is called the magnetic induction and others called the magnetic field. Okay. And I want to add one. That's the, since we don't have any magnetic monopole, that's 0. But instead of adding, if you don't know the sign for sure, then you have to be careful as to whether you add or subtract. So that's just a matter of choice. If you don't want to motivate the monopole at all, then you pretend that that is 0, and then you just instead of adding, you subtract these two equations. That's what you do. But then here there is a motivation for doing that at this moment. Okay. Oh yeah, since dual symmetry is sort of interesting, extra credit. Add that to extra credit. Read a little bit about dual symmetry. It plays an important role when it comes to string theory. You might have heard about string theories being, they were, even now they're good candidates for a bigger project, let us say, and this plays an important role in there. And most of the other forces we know is all based on electrodynamics, so they are just extensions of these concepts that we are developing. Okay, so if I do that, I get E dotted with del cross H minus of E dotted with, let me write epsilons, right? So this is, I can actually bring up epsilons. And what? And what? And that's equal to minus. I know myself. Yeah, minus maybe. G dotted with E. Right. And we also have minus of H dotted with del cross E. And minus of mu naught I pull out H dotted with E over dt, and that's all equal to, so this is not there, right? This is 0. Right.
dt over dt.
dh, oh yes. Thank you very much. Right. And notice at this point, I'll just mention it. Me pulling out this epsilon naught, the vacuum properties, plays an important role in this conservation derivation. And if there was a material property, if that was a material property, I cannot pull that out because material properties depend on space and time. And that becomes a challenge. And then you say that, oh, what is the conservation principle if you have materials around? And we do have it, but it's not so clean as we have it here. So that's one. That's one point you want to consider. Okay. If you have x times dx by dt, that's the same as d by dt of half of x squared. So I can use that in here and immediately get, and let's take it all to the right hand side. So I have d by dt of half E dot d plus half h dotted with b. Using this property and me taking this to the right hand side, I've taken these two, doing a lot of things in one step. Let me know if this is not right. So what will it here? Plus J dotted with E is equal to 0. So I've taken this to the right hand side, these two to the right hand side. So this also has to go to the right hand side. So it is plus H minus E. Did I do too many things at the same time? Is that clear? What I did?
So do we multiply both equations with minus and then add them together?
This is one equation right here. This is one equation, right? This was the continue. So that is one equation, and I took everything to the right hand side, or yeah, multiplied by a negative sign. Yes. So if I multiply with a negative sign and use this property, I get this. These two give you this. How about that? This here. This here. Oops. And these two, I think, is good. Okay. Okay. Let's process this a little instead of processing this. Already I see this, right? There's a time derivative of something. Seems like it's not gradient or something, so I have to process this. And there is something else remaining, right? So the idea is to write time derivative of something, divergence of something, and whatever is remaining is the source. Right? That's our goal. So let me do, since we said pointing vector, right? So let's independently do what is E cross H. And it's good to, at this stage, to do this in, if you want, index notation. Del I E J H K.
Can you explain to me one more time in the line above how we ended up with H dotted with
Yeah.
L cross E?
Yeah.
Yeah. So, let me just do this again, okay? Because it's an important step. So, okay, so let me take this all to the right hand side and write this as epsilon naught E dotted with dE by dt plus mu naught H by dt. That's two equations on the right hand side, minus E dotted with del cross H plus H dotted with del cross E plus J. Is this very clear?
Yes. Yeah.
Right? So I haven't done anything. I've rewritten that with some plus and minuses, right? These two use this property. X times dx is the same as x square derivative. That gives you time derivative, partial derivative with respect to time of epsilon naught goes through. So this is half 1/2 epsilon naught e square plus 1/2 mu naught h square, right? And minus of E is that clear?
Yes.
Right? And now I notice that epsilon naught times E square is the same as E dotted with epsilon naught times E, which is the same as E dotted with D. So this is E dotted with D and H dotted with B. Okay? That should be very transparent now. So proceeding then, let me take a small digression. So since I want to write this as a divergence, so let me check out what is E cross H. This is a scalar, so and epsilon ijk, right? So this an index notation is del I j hk. Derivative of two quantities, I can distribute it. That's equal to epsilon I j k del I ej, and then dotted with h r plus epsilon ej. If I want to interpret this as a dot product, this is already a dot product, right? So this will be del crossed E dotted with H. And this one, it is I and a K. I and a K are not coming in the right place, so I want to swap this J this way so that I can interpret it as a dot product. But then that swap gives me a negative sign. So that's minus of E dotted with del cross H. That's your sort of vector algebra coming in that we did 1 week or 1 or 2 weeks before. And this is exactly that's coming up here. Right? So that's very cool. So what we have now is d by dt of half E dotted with D plus half H dotted with D. And I'm writing it in this way so that if you ever do this for materials, then this has a meaning, right? But having said that, we won't have too much opportunities to do that here in the next 2 semesters. And this is plus divergence of E crossed with H plus J dotted with E is equal to 0. Okay. So now we have this definition already, right? So this is U now. It's a U is R and T dependent. Flux of U, let's give it a label there. It's a vector. It will be S. Pointing vector will be from S, which is a function of R and T. Very universal, right from the Maxwell's equation, only 2 steps. And I can argue that that's only 2 steps. We used a lot of steps there. But in principle, so our Maxwell, our conservation of electromagnetic energy is the rate of change of electromagnetic energy density is equal to the divergence or the flux associated with the pointing vector is the flux of energy. So let's write this dotted with S plus J dotted with E. That's equal to 0. So you want to interpret this. So this is rate of change of electromagnetic energy. Notice the point here, it is at a point. When you think of it, see earlier I did it for a volume, then you say that it is the rate of change of electromagnetic energy. Now this is electromagnetic energy density at a single point. This conservation principle holds at every point, right? It's significantly different when you think of it a volume and a point. It's like saying Gauss's law for a volume is good, but when you write it as divergence of E is equal to charge density, that's at every point. You cannot violate that at any point. So this is a local definition. So the language is, this is a local definition of conservation. Local means at every point in space, this is valid. The other one is called global. When you think of it as a volume, then it's called a global conservation law. This is a local conservation. Local conservation. Local means at every point. So this is rate of change of electromagnetic energy density. This is so in this sense, this will be the flux so this will be the flux of electromagnetic energy density, and we are left out with the third piece. Remember that is that will be interpreted as source and sink of electromagnetic density. How do you so let's interpret this a little bit. But first, let's write a statement. This is the or maybe first I should give an interpretation. That what is J dotted with E? Right. If it was a point charge, J is for a point charge. Point charge is J is equal to Q times V, right? And you need a delta function there, right? Delta function. R minus R A of T. Where if it is moving, it contributes at only one point. Okay. But notice, yeah, what is power? Definition of power in your Newtonian physics? Definition of power?
Energy per time.
Very good. So it's energy per unit time. Right. And energy is force times distance. That's the time. So apparently it is velocity times force, dotted with force. Right? If force is from an electric field, this will be equal to V dotted with Q times E. Right? So this is like Q times V is J, right? So this is force, right? So no, so this is power. So let's say power density. So power density would be divided by volume. Right? So this is power per unit volume. And the moment you bring in a volume, that's your delta function showing up there at only one point you have. And that seems to suggest that this is J dotted with E. So J dotted with E is, how will you interpret this? This is the work done by the force on the charge. Correct? So that's the way you want to read it. So whenever we say work, it is a work done by the force. Imagining the force to be an entity, it is a work done by the force on the mass. In this case, it is the charge. So here, this will be the electromagnetic energy work done on the charge, right? Electromagnetic energy density, if you want, density lost due to lost two charges, right? Lost two charges. Right? For example, if there is an electric field and it is making something move, right? You lost some energy there. Any kind of motion leads to losing energy. So that's so where do you lose energy? So the moment you're making something move, where can you gain energy? So you lose. Where do you gain energy from?
You don't.
You don't. Then
You either start with it or, yeah.
any other suggestions? You do gain. Where can you gain electromagnetic energy? Where can you create? How will you?
Adding charge.
The source.
How would you create electromagnetic energy?
Moving charge.
Oh yeah.
Moving charge.
And yeah,
Or
there's something more to that moving.
Quickly and
Quickly. What do you mean by quickly? Yeah, that's correct actually. Quickly. What does quickly mean in physics?
Accelerating.
Accelerating, right? Yeah, accelerating, yeah. So if you have a charge that is going with constant velocity, then it doesn't, then you don't radiate. Like how will you create radiation, right? Radiation is whenever something is in quote unquote quickly, right? It has to have acceleration. So this has creation also, so it can generate. So if it is accelerating, then you have, that's not very obvious here, but that we will see in the next semester. But there is creation also in there. Yeah, so that's a good place to stop. The next goal will be to write a similar equation for momentum, electromagnetic momentum, electromagnetic angular momentum. In fact, you can do various things, but we'll stop there. It doesn't always have to be a conservation equation. Any equation you can build out of Maxwell's equation has meaning to it. And we will probably stick to two of them. That's all. Thank you.
Thank you.
Excuse me, doctor, we want to clarify something. Last lecture yesterday, I lost connection in the last 10 minutes, so just to make it clear.
Yeah. Could you access the video later?
Yeah. But there was an interruption the last 10 minutes or so. So I left like I don't know how it looks to you, but that's what happens. Sorry.
Okay. No. I didn't look into the video. It's very hard to go into the video. I mean, this is long videos.
Yeah, I see.
Whenever I go, I immediately go into 20 minutes because that's one word. That's one page.
Yeah.
And then
Yeah,
I go to
I
40
just
minutes.
I want to just make it clear. That's
Thank you.
what
Thank
happens.
you. Yeah. Helps. Thank you. Okay.
So I have a quick question. So,
Sure.
like, the surface integrals are interpreted as the flux, right, of the fields, and then
Surface
from like an
integral of a vector. Yeah, of a vector.
and
Closed surface integral, or actually even open is flux. Yeah, that's correct. Yeah.
And then when you introduce force, say force is equal to Q times E, then you do a contour integral of it. That's when you get your work done on the charge, right? On a
Yeah. Yeah. Yeah.
So if you're thinking about it in terms of like intervals, then the force is like a contour integral of a vector.
Mm-hmm.
The surface is the flux, and then the integral is the Maxwell's equation.
No, actually, there it is slightly different. Notice there it is not a flux. What you have in mind is work done is equal to going from position 1 to position 2. It matters which position is, and you have to also give the path, right? Path, and then dl dotted with f. Sorry. So that's here. That's what is the contour, right? Path is a contour.
Yeah, but you need a charge now for the electron.
Charge, yes. So this is Q times E.
F divided by Q, or E Q.
E times Q, right? Q times E. Right? Yeah. So now tell me what your. Yeah. Actually, no, this is correct. Yeah, go ahead. So, yeah, what's
Well, I
your
was
point?
thinking like replace E with F, so now you have the force divided by the charge
Oh, okay.
instead of,
The charge. Yeah, okay.
and then you have force over a distance, L on your
Yeah.
integral. So that's just equal to your work, equal to the work divided by the charge.
Yeah, that's okay. That's okay. I think you were just saying this. Yeah, this is correct. Good. So this is actually Q times dl is J. So this is J dotted with E. And so this is a contour. Yeah. So this is, how do you convert this? Yeah. So what you would do is this integral Q dl, you have to switch over to volume integral.
Okay.
Yeah. Only then that becomes a J dotted with E, right?
So does that mean you'd have to do, so to go from a contour integral like the first one, you'd have to do Stokes' theorem to get a surface integral, and then how do you go from the surface integral?
No, actually, because here there's, okay, what happens is that actually this actually is along a, then you want to think of it as a current, because that's what you want, right? J somehow, right? So there is a, but here there is a area also. This is dl, right? And then there is a dA here, area also.
Mm-hmm.
And you have to connect the two. And I haven't given you enough information to do that, which we will do very quickly. Like, when do we do this? Whenever current density comes in a more necessary way, if you want. For some time, we will be working with charges alone. We won't work with current density so much. Magnetism is where it comes in, and there you write it. So I would say, yeah, this can be done, immediately can be done. But yeah, I haven't given you enough information that it's very obvious. It's not Stokes. Or should I say it's not? How about that? Yeah, think and come back to me. Yeah.
Well,
And I'm not very sure if it is not Stokes. Maybe it is Stokes.
Could
Yeah.
you just integrate that to the path function over an area? Just add a dA, like an integral over dA.
Oh, good point. Yeah. Think about it. Yeah. How about that?
It becomes a volume integral.
Yeah, but then work times area comes out.
Yeah.
Yeah, probably, yeah. Yeah, I'm a little, I see the connection, but I'm not seeing it right away. Think about it. That's the way I would put it. Yeah, yeah. I think you're in the right direction. Yeah.
What was your initial thought, Jordan?
It was just the way that he did the, using power and just thinking back, if you have energy divided by time, and then power density is power divided by volume. I was just thinking it in integral form instead of the way that he explained it. I was thinking like from a contour itself, you have a distance. You can get a force from distance times, or a work done by distance times a force. So then I was thinking from a contour, how would you expand it across, like he said, the volume? But the part that I'm not sure about is how you would get from the line integral to the volumetric integral.
Let me give it a thought. How about that? It's a very good point. It has to be related because this is a very hand-waving argument. This is more concrete because this should be work done by the electric field on the charges. That's the.
And I don't think it would be Stokes' theorem now because Stokes would give you a cross product instead of a dot product, right? It would give you. That's how you go from, the E dot DL to del or to the curl of E.
Yeah.
So it wouldn't be Stokes' theorem. I don't think.
Think about it. Yeah. Let me know. Yeah, I'm not immediately seeing it. I would go by this route because I know that is how you do it typically. But yeah, let me think about it. Okay. I don't have an immediate answer.
I have another question about homework. On 4D, the very last problem, where we had to verify the.
I can help you with that.
Okay. My intuition was that both were zero. That the time derivative of the current density is zero because your current density is constant for the point charge, and your divergence of the. Okay. All right.
It's not zero.
Okay.
So here is how it is, right? No, the row, right?
Yeah.
Rho. So rho is RMT undistrict. So this is Q times R. This is a coordinate minus the position of the charge, which could move around.
Yeah.
This can go around. So as this goes around, this changes function. Right?
Yeah.
D rho by dt. Right. Use chain rule. So do d rho over whatever is in here. Right. So it is R minus RA of t. Right? It's a chain rule, right?
Okay.
The derivative of this function, and then I have to do that function, right? Chain rule. Is that clear?
Yeah.
But the coordinate doesn't depend on time, it is this that depends on time.
Yeah.
And that is the position of the charge, so it becomes velocity. Even though it is partial derivative. This becomes minus, because it's there, and Q times velocity. And this is a vector, so this is basically a gradient. Derivative of this argument is the same as the derivative with respect to R.
Okay.
Right? Because the argument is decided by the R, right? Argument of R.
Yeah.
Same. So that's gradient of what?
Of rho.
Rho if I write it in this way, right? So yeah. If I remove the Q, then correct. Then leave it as it is. Don't proceed. Don't do anything with that.
Okay.
Right? So whatever it is, that is the case. Now do the gradient of J, right? Which is gradient, no, not gradient, divergence of J is Q times B, right? That is, what is it? This B times rho. Agree?
Yeah,
Velocity does not depend on the gradient. Like velocity of a particle is a one-point concept.
yeah,
It's not a gradient. You cannot talk about a gradient.
yeah,
That's independent of the coordinate. So this can come out, and since it's dotted with this will be dotted with. Sorry.
okay,
Which is exactly the same as this, but that's a first time, so when it's
Yeah.
added, it's
okay, okay.
So, yeah, I mean, I think the confusion that comes is at this stage, you think, okay, I have to keep proceedings. Right? But you stop. But
Yeah.
the idea is just to show that this is actually valid.
Yeah,
My confusion still just comes with integrals with delta functions and stuff. I'm really struggling with that, figuring out
Oh,
what we're supposed to do. I don't know if
Um,
there's a good resource for that, but I can't really find.
well, I did not do an integral, but yeah, okay, let's do this. Okay. Oh.
Couldn't you just have integrated the let me go back to the problem.
Integral is not sufficient because we are treating it as a local statement. The moment you integrate it, it becomes a volume. Right? Then it is a global conservation equation. Continuity equation locally is slightly, like I don't want to say more powerful, but has a slightly different content than a volume integral. Like Gauss's law in integral form and Gauss's law in differential form. Of course, everything can be derived from each other, but Gauss's law in differential form has a different meaning slightly from Gauss's law in integral form. Right? So this is all local. I didn't integrate at all.
Okay, I just did that wrong, I guess. I guess I just didn't see that idea.
Yeah, this is a little tricky because one thinks that, oh, what is this? That's an abstract entity, right? Everyone wants to have a more physical meaning. And this is actually having a meaning in a sense that is the dipole moment and all that we will talk about later. Yeah. So, this will become a dipole moment. Or dipole moment has the same concept. Maybe that's it. Is that all?
yeah, thank you.
Okay. And delta functions. Yeah, this is the second time. I mean, it shouldn't be hampering. Yeah, okay. How about this? If you can do me a favor, on Monday, on Monday we teach, right? Let me spend half an hour on delta functions. Okay.
Okay.
Let me clarify this. That shouldn't be. I mean, it's not. I struggled a little, so I think it is throwing you guys off because I struggled. I use it at a very simplistic level. So at the user level, let me tell you some examples which clarify. Okay.
I kind of feel like the integration of delta functions is not that hard. It's quite easy. But when I have to differentiate delta function, yeah, I don't like it.
True. That's agreed. I mean, this problem, I agree, is at this point, why would you stop them? What intuition makes you stop them? That's a little tricky. The only reason is that you want to do this here also. And, yeah. That I see. First time when you're doing that.
That's just being sloppy. You get the same thing in both terms, you just cancel them.
Yeah.
That is the goal.
Yeah, well,
You're
the way that
but
you worded the
yeah,
question,
efficient
you were
doesn't-
guiding us to do that. It was like, here's the function for this, here's the function for this, show that they're the same. So,
Yeah, I see that. But then homework is also to make you feel a little, think along various directions, right? So yeah, I know what you're talking about.
that's good, thank you for the clarification.
Reasonable?
Mm-hmm. Yeah.
Yep.
Okay.
Thank you.
Okay, Michael. Michael is very unpredictable. Sometimes you're here, sometimes you're there. I kind of.
Right.
Others are very predictable.
I don't know, I haven't been predictable.
Yeah.
I'll come and go.
Yeah, that's true. I think
I usually,
I say Michael's is very weather dependent, I think. It is not a complaint, I'm just making a small joke out of it. Here, so.
hey, one of you should stay there so I can stay here.
Oh yeah, Michael decides. So whenever Avinash wants to come in,
Yeah, one of you guys has to be there.
Okay, yeah. Bye, Michael. Bye, Jordan. Anything else, Aliyah?
No, thank you so
There
much.
is even rules.
Huh?
There's even a function of rules.
Function of poles, what?
Like pole. Hey, what does everybody think? A, B, C, D.
What?
They have functions for poles.
Yeah. Oh, you can use a poll on Zoom.
I didn't know about that.
Yeah.
What is a function of a pole?
You can use, there's a feature on Zoom